for an AV company, you want to also determine what the vulnerability is. So that's optional, but most people, they don't need to do that. So, all right. So there are two ways you can do it. You can do static analysis. Basically, what you do is you go into a hex editor and you figure out where the shellcode is, and you disassemble it and you read it by hand. You read it manually. Because sometimes the shellcode is pretty complicated. Like they'll do sometimes the decryptor stuff. It's like pretty big and it does all these weird stuff that you don't want to keep track in your brain. So for that, you can use dynamic analysis. So you can actually run the shellcode live, and I'll show you how to do that. So this is the first method. This is from Hugh. I blacked out some of the stuff because I didn't think that was important. So this method is actually pretty cool. So you open up in Hugh, and any of you guys recognize any of these characters? So the first thing you see, the E with the like forward accent thingy, that's an OX90, which is a knob. You see the 3, and then like I need to use this. You see this 3 thing right here? So you view this in a hex editor. I use Hue because you can see these things. So you look for these common patterns. You look for like sometimes the knob slice, if they have a huge knob set, so it'll be very obvious. In this case, like the E right here. So you go there and you disassemble, and if it makes sense, then it's good. If it doesn't make sense, then you go to the next one. The next thing you should pick up is these 3. 3 in hex is OX33, and 33 in Intel opcodes is part of like XOR instructions, which typically have 33. So a lot in decryptor stubs, there'll be like an XOR. So you see a lot of XOR. If you notice, you see here it is the 3. Here's another 3. Here's another 3, and a whole bunch of other points. So so they use XOR a lot. And another thing you should notice is this I right here, the I with the 2 dots on the top. This is 8B. So 8B in Intel opcodes is like move instructions. So a lot of shellcodes, obviously when you write assembly code, you need to have moves and stuff. So you can, and that will involve, it will be 8B. And so you can spot these out. And if you notice, there are a lot of these I's right next to each other. So you know that when you have a lot of moves close to each other, there's a high probability that this is probably legitimate code. Yeah. And another one you should pick out is this one, these 2 things right here, the 0O with the delta, like lowercase delta in Greek. This is actually EB, which is a jump. So jump call pop, you'll see these things. So here you see 2 of them. And the next one you should know, this thing right here, the circle with the line. The circle in the line is EA. EA, it's a call. So typically they'll do a backwards call, so it'll be E8, blah, 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 FF, something like that. So you spot those, and it might be a real shellcode or something. But the thing is, when you actually, like, most people don't do this because this requires like doing it like 1,000 times for you to recognize these patterns. But when you see these characters in juxtaposition, there's a high probability that it's probably shellcode. One of my colleagues, Christian, he's a virus analyst, and one day he was analyzing some of this stuff with me, and he used Hue, and this guy literally, he just scrolls through like page down, it's like, oh yeah, that's shellcode right there. And I asked him, what the hell, dude, how do you know this? Yeah, and he's like, oh yeah, dude, like the uppercase E with the forward, the accent mark, that's like encrypted, it's like ingrained in my brain, so I just spot it out. It's crazy, but it works. So you can also impress like girlfriends or something like that with that method too. So, well, a lot of us, like, if you haven't done it for a long time, then you obviously can't do it that fast. So you got to memorize some opcodes, and so you got to spot out. And you remember EB, which is going to be a jump, E8 call, 8B typically move, 5B. Most of the opcodes in like push or pop, they'll be like in the 5x range, and E2 is a loop. So like here. And also the 33 range, most of the XOR opcodes will start with 33. So when you see all this stuff close to each other, you have an intuition that it's most likely that they're trying to do something that's like shellcode-like. So most of the time I ask people whether they recognize, but I'm not going to ask it here because there'll be like an insult or something here. So anyways, and another thing they will use typically though, because to access the base address of kernel 32, they need to look at the tab. So they need to access the tab, which is FS30. And so anytime you, in Intel assembly, anytime when you access a segment, like for FSGS or whatever, you need to have a prefix. So this is a 64 prefix. Anytime you access any instruction that access the FS segment will have a 64 prefix. So you see a 64 and then followed by an 8B, you know that that's a move involving the FS segment, and so you disassemble it. This 64A130, that's like move EAX, like FS30. And then the next one, 648B1D, that's like move to EBX. And the last one, D97424 blah, a lot of the floating point instructions will start with the D9. So like FNSTNV is another way to get the EIP. And this is used in Metasploit encoders, so you can actually spot this pretty easily. Yeah. All right. So once you determine the shellcode, obviously this I'm gonna go through. These are dynamic analysis techniques. For static techniques, you just page down when you read. Once you identify the shellcode, you just patch the first few bytes with OXCC, which is N3, and then you at startup Office, you attach a debugger to it, and you click on the document, you open it up. And if you identify the shellcode correctly, then you'll hit a breakpoint. But if you didn't, then you'll be screwed because then the shellcode will run, right? So it's important that you run this in a VM or whatever. But of course, everybody here knows that. So yeah. The method 2 is, this one is quite common in the AV business. What these guys do, they'll have like an executable stub. They just copy the shellcode to the entry point, and they load it up in their OllyDBG or whatever, and then they single step through it. So that's pretty easy to do. And it's actually very logical to do that. But the last two methods, if you notice, we don't open any file at all, right? The reason why is, because we don't open any file, when the shellcode tries to brute force a file handle, it goes into like an infinite loop, and it sits there and it locks, and then eventually the application crashes. So sometimes, then in most cases, if it can't find itself, then it's not going to be able to extract a Trojan. It's not going to be able to extract a clean document. So you're not going to be able to get the most juicy part of the sample. So the next two methods, you're going to be able to do that. So what you do is you save the files like wherever .bin file. You open up Notepad, calc.exe or whatever, like anything you want, any process you want. You attach WinDBG to it. And then you call it .dvalloc. dvalloc, all it does is it allocates a block of memory with read, write, and execute permission. And then you call readmem, and then you basically, what all readmem does is reads the content of a file into memory. And that's all it does. And so with these two things together, you can say that once you identify the shellcode, you know the physical offset relative from the beginning. And you know where the file is loaded. So the shellcode address is going to be wherever the base pointer plus the physical offset of the shellcode. And then once you figure that out, you just set EIP to that address, and then you single step. And then that's it. Then you'll be like running real shellcode inside debugger. You can also use this method to debug. If you're writing your own shellcode, you can use this method to debug as well. Here it is in action in WinDBG. This is very useful. So if you use WinDBG, is like extremely useful. You should all use it. Method 4. This one, it's pretty easy. Okay. These methods assume that, how do I say this? Sometimes the attackers will know exactly what version of Office you're using, like what locale you are. For example, if they're attacking a German version of Office, they'll like build the exploit according to that. So, but sometimes if you're an AV analyst or whatever, and you like, I don't know, you live somewhere in Japan or whatever, and you don't have a German version of Office, or you don't even know what locale they were targeting. So when you double click on it, it won't run, right? It'll just crash, and you have no idea what's going on. So how are you going to extract the Trojan? So you try to emulate the Office environment. So all you do is you open up a hex editor or like anything that opens the file. You can write your own program to open the file too. And you attach WinDBG to that file, and then you do DVL. You do the same thing. And the advantage of this is that because you open the file, you have a file handle. Even though it's not Office, it's still a file handle. It's a file handle. So when it brute forces, it'll find itself, and then you'll get the Trojan and the clean document. So this is probably the best method. I use this method every day, I guess. So it's very useful. All right. So that's how you analyze. That's pretty much it. Because most of the time, once you extract the Trojan, all you do is then you do the analysis on the Trojan. You don't care about the office sample anymore. So how to detect this stuff? It's actually kind of difficult, but not impossible. So you need to figure out if you're an IDS, you got to figure out, okay, is this file an ODSS file? If it is, then do something with it. And the way you identify an ODSS file is by the first 8 bytes. It always has DOCF11E0 and blah, blah, blah. And then you fingerprint the application. And by fingerprinting, I mean is this a Word document? Is this a PowerPoint document? Is it an Excel? Blah, blah, whatever. And the way you do this is you read the stream name. For example, you see an OD file with the stream name PowerPoint document stream, then that's most likely to be PowerPoint. If it's Excel, they'll have workbook streams. If it's a Word document, you see a Word document stream. So based on that, you can determine whether the application is Word or whatever. And then you parse the stream content like I showed you earlier. And then you determine the affected records. Most of these bugs are actually in the parsing of the records. So if you know what records are affected, you can actually write a signature to detect this exact vulnerability. And so the UFP rate will be much lower. So here we go. So you can download the specs from this website, or you can just go to live.com and search for Microsoft Office specs. It's usually first or second hit or something like that. And so given the documentation in here, you can actually write your own parser. And like I said, it gets updated quite often, every month, sometimes every 2 months. So it's very, very useful. And this. So map is, let's say that you don't have your own parser. Let's say that you try to reverse engineer the patch. But most people, when you bin diff a patch, you can figure out, okay, yeah, this is a buffer overflow. But in Office, in order to exploit the vulnerability, you actually need to know what specific record is bad, right? So without that knowledge, it's very difficult to craft your exploit. So you need to know the file format so that you can write your exploit. And bindiff obviously is not going to show you that. And at the assembly level, it's very difficult to figure out what type of record what type of record you need. So in order to write good signatures, you need to figure this out. Because if you do generic, you'll get FPs all over the place. So you have 2 options. You can either reverse engineer the patch and I don't know, pray and work really hard to figure out the the record type, or we'll give you the vulnerability details. So if you work for an AV or an IDS company, we'll provide these things. And this is the Microsoft Active Protection Program, aka MAP. I actually work on the team the team that produces this data. So I deal with mostly PowerPoint stuff. So if a PowerPoint, anything to do with the kernel, network stack, RPC, whatever, it'll be me. So if you can complain or hug me if you want. All right. So what do you get with this MAP program? You get a technical description of vulnerability, a repro file. I'll actually generate a file because I already know what the record is. A repro file, if it's a network vulnerability, I'll give you a packet trace. And then, then it'll be a no-brainer. And then we'll also give you a crash dump, or even a stack trace, a disassembly, and sometimes I'll include annotations of the disassembly, because obviously I can't give source code. So I'll annotate the disassembly so that people understand, what the vulnerability is. And also I'll give detection logic, which is implemented in this detection logic. Basically, I'll give you it'll be a C-like program that you pass a file in and you run it against this program, and it'll tell you whether the file is vulnerable or not. And most people, a lot of our map partners, they'll take this, they'll translate it into their own engine language because it's very C-like, and then they just deploy it. So here's an example. This one is pretty old, so I can say it now. This is an Excel vulnerability, and this is what you'll get. This is a technical description. We tell you that this is an uninitialized stack, uninitialized memory vulnerability. We'll tell you that the exact records that are being affected, and we'll give you the detection guidance. And with all this stuff, you know, if you're not lazy, you can translate a lot of this. You can take this, translate to your IDS or AV. Yes?